So welcome to the Imaging SIG meeting. And tonight we're going to talk about 3D printing. I wanted to talk about the format a little bit. We're going to have three presenters. I've asked them to talk 10 minutes. I'll interrupt them at 15 minutes, but shoot for 10 minutes kind of thing. And I'd say we do this without questions, have sort of three presentations like that for a half hour to 45 minutes. And then we'd have another half hour or so of interaction where folks can ask questions, make statements, do whatever you'd like. And we'll try to end it in like in an hour and a quarter, hour and a half, sort of in the timely way. I sort of wanted to give a shot at a fixed time limit for these meetings. So that's my plan. Welcome everyone. And I guess that's about all I wanted to say. So, Joe, you about ready to get started? It seems like we have a quorum now. So our three speakers are Joe, Paolo, and Glenn, and I assume in that order. So take it away, Joe.
Okay. So yeah, thanks, Hi, for inviting me and for hosting me. That's really a new one for me to actually speak in California today. Hi told you already, it's given us a very limited time. So I called this here a futile attempt of an elevator pitch because he's given us about as much time as it takes Jeff Bezos to go into the stratosphere and then come back down again. What I want to tell you about 3D printing, first of all, is a little bit of an introduction or an overview for people who have not used a 3D printer before. So this is basically my setup. It is one of the cheapest ones you can have, but also one of the most versatile ones called an Ender 3. And what you can see here is that's the 3D printer. That's the print head in here, a spool with the thermoplastic material. I've got a Pi 4 in the back to keep to have a little camera in here to keep an eye on the printing process. I can also record it, and that's really all there is to it. So a 3D printer is really not much else but a clunky inkjet printer. The only difference is that it's not using ink, but it's using thermoplastic material, which you can weld, which is welding together to form a three-dimensional object. And both operate on the same principle. A 3D printer also uses stacking software to create a 3D image, and that's not unlike what PixInsight and Deep Sky Stacker are also doing with individual image frames, but in reverse. So basically, if you've ever used an inkjet printer, and if you're using PixInsight and Deep Sky Stacker, you already have all the ingredients in place to productively use a 3D printer as well. So 3D printers are incredibly versatile, and I cannot understand really how I could ever live without one. And I'm going to give you a little bit of an overview on that, and we can talk about that later. So supporting the astrophotography hobby is really only one small application 3D printers are good for. Ask me more during the discussion session about this. And the best thing also that I don't want to forget to mention is all the basic software you need to run your 3D printer is open source and is free. So you're not really risking a lot. The printer I showed you costs about $200, and that's all it takes you to get into this hobby and start printing whatever you like, not just astro here. So this here is an image of one object, for instance. It's a Barettoni mask. So this is images created in a software called Slicer. And that is the software which prepares the data to being sent to the 3D printer. So pretty much the same thing as what you would have in the print menu. And this here is one of the things which I've printed is a case for a Pi 4. Lots of these things you can actually download directly from the internet, so you don't have to design them themselves. There is a fantastic place called Thingiverse and various others. There are all sorts of 3D printable objects are deposited, and you just download the files for this. This one here I have modified so it actually fits my purposes. I cut in some extra opening and so forth to make it more accessible. and to mount it on my rig. Okay, so this is another object which I'm going to show you shortly. This is a frame for a ASI 1600. The camera would fit in here. My little guide scope would fit in up there. And here I've got a rail where I can mount my autofocuser, and I'm going to show you the pictures of those in a second. This is what this looks like, what I just showed you. So an action. So I used 3D printed this file, which I designed on the computer using FreeCAD, very simple software, not more complicated really than Photoshop. So if any of you can operate Photoshop or Illustrator, you can also operate 3D printing software. It's not any harder than that. I clamp in here. I designed it so I can clamp in my ASI 1600. Here's a 135 millimeter lens mounted to the ASI 1600. I put this gear ring around it so that I can connect it to my autofocuser here. And that is just driven by a small toy analog motor, which then is controlled by ECOS. Hai has already told you probably a lot about ECOS and the software package it entails, and a driver called FCUSB. So I can autofocus with this here, a standard 135 Nikon camera lens, which I got on Amazon for $50, attached to an ASI 1600. And that gives you very nice pictures of the night sky. So this is what I actually took with this about a year and a half ago. So obviously the Orion region with the horse head. And that picture was taken with the ASI 1600 mm and the 135 millimeter, I think it was the 135 millimeter lens. And this autofocuser, which I just showed you, 3D printed. All just put together from some really basic pieces. You could also do the same thing with a DSLR and a regular DSLR lens. So this is the next step up. I wanted to use that same 3D printed system here, in which again, it's for an autofocuser, but I've now adapted it to a white cat. Very similar, basically the same design as a space cat or a red cat from William Optics. And as you know, that's a helical focuser. So I had to clamp this gear ring here around it. I put an extension in, so I have a bit of a higher leverage. And I used a larger motor, which I put onto the rail because this helical focuser here has more resistance, and the small motor wasn't really cutting it. But this is still an analog motor. The next step up, and here is this the holder for the Pi 4, which I printed, holder for the FCUSB, for a powered USB hub, and all of this here is mounted together and clamped to the leg of my tripod for a CM25. Then I wanted to get a little bit more sophisticated, wanted to get away from the analog motors for my autofocusers. And so I changed that and used basically the same design again, but now to mount a stepper motor to this. This is the setup, the SEM25. This rail here, stepper motor is there, drives that gear attached to the helical focuser of the William Optics white cat. Okay, so this here is again another piece which I 3D printed. It's a case for the electronics for the autofocuser. So what you're seeing down there underneath all those wires is simply a little board with an Arduino on top of it. You're seeing this, the CPU unity of the Arduino right there. And here is a stepper motor driver. The software for this, as well as the design, is also freely available. So the entire setup here, including the thermal probe. So you get refocusing when the temperature shifts by more than a predetermined amount of degrees, in my case, 2 degrees centigrade. The entire setup here has cost me about $25 to put together. This is the setup then in action at night with everywhere you can see now everything, the 3D printed holder for the Pi 4, for the SSD, which is stuck into a sleeve back here, the powered USB hub, then an adapter to put the polar alignment, the pole master mounted onto the tunnel, the 3D printed autofocuser up here, and the White Cat telescope. So almost everything holding this rig here together has been 3D printed. Okay. So now then next I wanted to adapt that to my ED 102, Explore Scientific 102. So that for that I didn't have an autofocuser yet, so I printed the new autofocuser control unit, but now I needed to have a new frame to drive the focuser on that 102. And this is a picture which you see now from the bottom of that. So I designed the clamp basically, which I can just screw onto, clamp around the base of the telescope between the focuser gears. And so there's nothing which is actually screwed onto the telescope. So this is just a pure clamp construction. And put some gears in here. The stepper motor is here driving this little gear, which then drives a large gear, which is attached directly to the fine focus knob. So I didn't have to take the fine focus knob off the shaft. This is just stuck on and held in place with 3 screws, which are threaded through the 3D printed gear here. Now, you wonder probably what the spring here is. So turns out that the Crayford focuser in the ED 102 has a tendency for slipping, and that would be the same actually with a commercial focuser as well. So I use this spring here in order to take weight off the filter wheel and the camera, so the focuser doesn't slip when the telescope is pointing straight up. So the spring really just helps, supports the weight of the filter wheel and the telescope. And this entire setup here really works very well. So this is a screenshot here from the ECOS control panel. I assume that Hai has already told you all about the software package. Down here you can see, and he actually designed this surface here. And down here you see the V curve of the focuser, and the autofocuser, which I just showed you, hits the absolute minimum of the V curve every time. You can see here the yellow spot. So extremely reliable, all from self-designed 3D printed pieces. So this works really well. And now you're wondering probably, well, you know, I'm environmentally conscious. I don't want to waste a lot of plastic and contribute to the environmental disaster we're already living in. Well, I've got some good news for you. So the material which I'm using, and which is the most popular one, is called PLA. So that stands for polylactic acid. And that is an organic material. It is fully compostable. So whatever I'm not using goes into my compost pile here in the backyard. And it does take a long time and you have to cut it up, but the material is going to be completely biodegradable, so you don't have any plastic waste. Okay, so with that, I'm through before Hai cuts me off. Hope I stayed within the 10 minutes, and happy to answer any questions to you later.
Thanks, Joe. That was incredible. You met under 15. I'll give you that. No. So it's fine. 15 was the hard limit. 10 was the goal. Okay. Well, let's move on to. Is it Paolo next? Paolo. Let's move on to Paolo. Take it away. Unmute and present.
Let me share my second screen. Okay. You can see my screen now?
No.
Not yet, Paolo.
Here you go.
Okay. Okay, so from where to start? From the beginning, I have a different kind of 3D printer, the one that is called a Delta, because the movement is not XY Cartesian like the one of Joe, but has these 320 degrees spaced three motors, and that's helped to move the head. What I have using as a filament, just to, sorry Joe, but I don't like the PLA because from my point of view, okay, that saved the planet, but is a little too soft, especially in terms of temperature, because here in the sunny California, and I think also the same in Texas, where you are, if you leave the scope out like I do during the day, also if covered, the PLA can bend if you are under the sun. So normally I'm using or ASA. Please don't ask me to read the very cryptic chemical name from the acronym is coming, or the PETG. PETG is a good compromise that I'm using a lot in this moment because it's the same plastic that used for the soda bottles. And that is very stable and relatively, let's say, stiff. ASA is a very close friend and cousin of ABS, and is very stable in terms of ultraviolet exposure, so it can be left outside without many problems. Okay, what I'm using for designing, I'm not using the software that Joe was mentioning, but I'm using another approach. I am let's say, a programmer by trade, so this kind of OpenSCAD and other open source is very useful for me because you use a sort of C that has many basic primitive circle, cylinder, these kind of things. And with that, you construct the things that you are designing. I'm using Ultimator Cura for slicing. The slice is the process that is a sort of, talking about computer similitude, is like compiling a high-level program. Take the product of the previous program and let's say translate in order for XY movement of the head that depose the filament. What I am done, okay, you see the first image previously, and now that's the let's say the realization. That's a box for an Arduino controlled flip-flat look-alike. Here there is a flat of a square of LED, and this is thick because you need to have a sandwich of various material in order to spread evenly the light. That's another example of use of ASA for building. Sorry if the dust, but it was just polished. And so that's a classical ring support for an 80 millimeter, no, actually it was 70 millimeter, was the Jerry one. 70 millimeter scope on a Vixen dovetail. Another, this I think is my complex so far design is an XZ stage that I plan to use with the OTEC for setting up a scope, and I need to translate the laser. And so that's is a translation in a vertical here and in a horizontal here. And that is quite complex because it has gear inside and slide, dovetail, and jib to strengthen and close the dovetail play. And that's quite complex. Another little things was a non-rotating focuser, and that was a very, let's say, challenging and interesting design because I have no idea how to do it. So I researched on internet how a lens, a camera lens, are constructed. And I say I reverse engineered the idea, and I construct. Those are 3 pieces. One piece is here, the second one here, and the middle one has the 2 threads, one clockwise and the other counterclockwise. So when you turn the middle one, the 2 external pieces can, let's say, be shortened or elongated. And I use that on a off-axis guide here for focusing the camera without losing the orientation of the camera sensor. Oops, sorry. Okay, next one was a support for an old Tamron catadioptic for an Olympus attachment, and I used this with micro focus control here in order to focus, and that was a manual, not a motorized. And I have different bases, and I did a lot of testing in order to stiffen the base and avoid flexure with these, let's say, ribs that I discover is definitely better to have this kind of ribs instead of having a thick material like here. Now you see the ribs here. That's a Losmandy dovetail. Another one, okay, that was of course, in this moment, and that was the batten of mask that I printed for that one that High is showing in this moment, and these one instead are smaller for my Guider AT-ST short tube, and that's another use, and that's it. And basically I'm using the 3D, or beside of course a bunch of cover, extension, boxes for other project, for related project. Is useful. Of course, sometimes you have to plan very carefully because let's say the 3D printing has a problem to print without a support some pieces, so you have to better, let's say, plan for that. But it's very useful, and that's it.
Well, thanks very much, Paolo. Again, unbelievable stuff you guys are building. All right, Glenn, take it away.
Hey, okay. Share my screen here. Paolo needs to stop. Okay. Okay, can you see that?
Yes, Glenn.
Okay, great. So I guess I don't have a picture of my printers, but there's behind me here is the big one that's enclosed, and that allows me to use hotter materials that require more heat, and that's an enclosed printer and keeps the part warm all around while you're printing. So I'm prefer to use nylon carbon fiber. So these parts that are this gray one here and this one that look kind of rough are this nylon carbon fiber, and then the ones that are more polished are probably ASA, and this dust cap here is or lens cap is kind of flexible rubber. It's TPU is that material. So I have that printer, which I use for the nylon carbon fiber, and also buried back there amongst all the Astro junk is the same Delta printer that Paolo has. So you see here a variety of different things that I printed, dovetail clamps and various ring mounts for lenses and telescopes and whatnot. And I talked about the lens cap or dust cover. And then these are threaded parts for extensions and prototyping things, and also for attaching moonlight focusers to various OTAs that without having to buy a special adapter or the specific moonlight flange for that. So let's go on. Yeah, so I'm Glenn. Hi. You've probably seen this before, but here's my email or what if you want to reach out, that's fine. So I'm just going to kind of list a bunch of stuff that I've done. So Paolo and I have kind of built up a thread library of each time we need a new Astro thread, then we add that to the library. So these are the ones that are in there now. And I think the most ambitious one here is that the club has this Vixen 140, and I wanted to remove the stock focuser and use the moonlight focusers that I have so I can autofocus. But this is a Petzoval design, so there's a rear, this black piece here that I'm holding is a rear lens cell. So there's a lens inside that, and that has to go down inside the focuser. So this adapter had to have 3 threads on it, one for the OTA itself, one for the focuser would be here on the right, and then this internal one for the rear lens cell. And you can see here that was a 55-hour print because I printed it in solid plastic in the nylon fiber. So that was a multi-day print, and that's assuming that you didn't have any errors. So I think it was maybe 4 tries before I got through the whole 55 hours. But okay, so some other things. I made a beam splitter for spectroscopy so that I could, have a camera on there for plate solving, and then the majority of the light would go through to the spectroscopy camera. And then it occurred to me, well, that's pretty much the same as on-axis guider that uses a cold mirror instead of a beam splitter. So I did a bunch of experiments semi-successfully, I'd say, with the cold mirror, and that's where the visible light comes in and hits the mirror and goes up to your imaging camera, but the infrared light goes through the mirror to your guide camera here. So that's an example of what that looks like. And that way you get the full frame guiding of, the full frame is available for the guide camera. And then also there's an interesting side effect, which you can use. There's astigmatism because you're going through at this 45-degree angle, and you can actually use the shape of the stars with that astigmatism to build an autofocuser based on that. So there's Innovations Foresight ONAG is the commercial version, and there's software available from him that that does that autofocus, real-time autofocus as you go through the night. Some other mechanical stuff is for the planetary. I had a flip mirror that I wanted to automate from inside the house, and it's maybe a little confusing here what's going on, but the flip mirror has a knob on the side of it that you would normally turn, and so I was gluing that to this motor here, and then I actually used the pointer on the knob that's part of the flip mirror to hit these little micro switches here and tell me which position it was in. So that's what that was about. And here's a before deciding to switch to the moonlight on that Vixen. This is the Vixen stock focuser, and I did some experiments trying to automate that focuser, but I wasn't happy with that. But this is a 3D printed clamp here that mounts a inexpensive stepper motor, and you have the union there to the stock focuser. And then this one was a focuser for a Mac CAS or an SCT, where you have the knob sticking out of the back of the OTA, and there weren't any screw holes or anything placed to mount anything on. So I made this ring where the visual back, I guess you would call it, screws down on the OTA. So it screwed down over this ring and then held the mount for the this same type of stepper motor here that would then connect to the focusing knob. Some other things. So here's my version of the camera lens focuser that we saw. So the stepper motor mount on the small rig here is 3D printed, and the gears are 3D printed, and this material here is that soft TPU, so it's kind of a little bit like a rubber band. So you stretch it over the lens, and then it just friction fits. And so that's how I was doing that. And then later, this huge monstrosity here is my DIY rotator, and so it has a lot of 3D printed parts to hold the big massive stepper motor with gears steady. And then you can see here there's a belt, and this is the gear that press fits on the extension for the focuser. And so the whole the focuser, and this is the commercial ONAG, and here's the bottom of the filter wheel. So this whole everything here rotates around the back of the telescope, and the 3D case here for the electronics, it's Arduino, and the solenoid driver and all that is 3D printed as well. And then going back, this scope here on the bottom right, this was the first scope that I had. It's a department store kind of, or mail order type scope. It's a Mac CAS, actually still good for planetary, F13, but it has this knob that just refuses to I can't figure out how to get that thing off of there. And it's nestled in amongst this plastic housing to where you can't easily attach anything to it. And if you try to adjust this thing when you're visually observing by hand, as soon as you touch that, everything wiggles around, and you can't tell if you're getting in focus or not. So this was my first focuser attempt. So this is actually just a DC motor in this case. And again, the TPU material forms a rubber band type belt that friction fits very thinly in the thin gap between this cowling and the knob. And so that worked. And then there's 3 of these rings, two of them to mount the scope and one of them that's flipped around to mount the solenoid, or sorry, DC motor case on. So that was a lot of kludge on that one. So just random other things. This is a Newtonian collimation that can also be used for RCs. So you put a laser in here and then you have this diagonal surface to make sure the laser goes back in the hole as you line things up. Besides all the threaded parts, I've also made non-threaded spacers and washers and things that sometimes are handy for making sure your camera rotates to a certain place versus maybe you don't want it to go further than that for aligning things. And here's an example of a strain relief or wire guide. And it also, I put sort of degree markings on it and glued these levels on it. So in this case, you know, if the SGP tells me to rotate, 60 degrees or something, I can go out there and see what I'm doing. What else? Oh, for Bruce, for his Raza, I printed some transparent storage boxes for the 2-inch filters that go in the tray filter system for the Raza. And then sort of on a completely different note here, I was trying to experiment with various 3D things, 3D printing being one of them, of showing astrophotos. So this is something called a lithopane, and it's designed to show light through. And so this is my tadpoles image here, and this is what the lithopane looks like. And then I put a transparent image of the tadpoles behind it to get the color, and that's what it looks like. So it was an okay experiment, I guess. What else? Oh, so that's pretty much it for me. Yeah, so
All
I
right.
think we're ready for questions.
Yeah, thank you, Glenn. And thanks everyone.
Sure.
All right. Well, let's open it up for questions. Please, why don't you just try to go for it? And if it gets unruly, we can raise hands, but let's just try, whoever wants to talk, go ahead.
I can stop sharing.
Or I can ask the first question, but I'd rather get a volunteer from the audience. Nothing burning. Go ahead, PJ. Or it isn't PJ, it's Rob who's unmuted. No, you haven't unmuted yet. I'm sorry, I'll shut up. Somebody.
Question, all amazing stuff. I don't have a 3D printer. I'm planning on getting one at some point. But for all the materials that you guys are using, what's the cost?
Yeah, so the one which I showed you, PLA, okay, so Paolo doesn't like PLA that much, but it really is, first of all, the simplest and probably also the cheapest material and fully biodegradable. That's why I like it. So a 5 kilogram spool of that costs me $90.
Okay.
So 5 kilograms you can print a lot with.
Got it.
Yeah, normally cost from 20 to 40, 50 a kilo. If you go on the exotic, like the carbon fiber that Glenn was mentioning before. But again, a kilo, and a kilo is a lot of filament.
And you
So
said
like how many kilos have you used in your career, Paolo?
Oh, but I have a bunch of, for the astronomical, I think 2-3 kilos, not more. But
Yeah, that sounds about right.
you know, a lot you use at the beginning when you throw away a lot of things because you make mistake and
learning curve. Yep.
Learning curves. Yes.
Got it.
Yeah, and some of this, you're prototyping, right? So you might make something and then later replace it with something in metal. But for durability or what have you, but you know, you're experimenting and you're trying things, so that gives you that capability. Or if you're desperate to hook this thing to that thing and you know the stores are closed or whatever, right, you can build something in an hour or so, or a couple hours.
Yeah, part of the learning curve that helped a lot the junk pile is the fact that normally the circle, or better the cylinder, or the hole, the cylindrical hole, are different from the nominal size, because you have to think that at the end of the story, the 3D printer head is moving in a rectilinear way. So a circle is approximated with a lot of little steps. And so that means that the cylinder tend to be smaller, bigger, and the hole tend to be smaller in diameters. And that's create a problem, especially if you are printing, I don't know, an M48 thread, and that's sometimes you have problem, and so okay, junk, and that's create a lot of
So PLA is biodegradable, but the other material, can it be recycled? Or what can be recycled? Or what could potentially be shredded and probably sent to somebody for recycling?
I mean, the other are all plastic that normally are recyclable, because the PETG, for instance, is as I mentioned before, is a normal plastic soda bottle. So that can be recycled.
Well, and if you're really hardcore, you can take all your scraps and melt them down and turn them into filament.
Or
right?
use soda bottle, for instance.
Yeah, or you could make a soda bottle.
No, you can use soda bottle too.
Oh yeah, and make your own filament from the soda bottles. Yeah.
Yes.
There you go.
That's, I mean, the problem is that the filament is normally two standard in diameter. One is 1.75 millimeter, the other is 3 millimeters. And for the precision of printing and avoid any, let's say, blockage of the mechanism, you have to have a very precise dimension in terms of diameter of the filament. And so if you do by yourself, honestly, I don't know if you are able to reach easily that things. Talking about that, I remember that Glenn at a certain moment you were trying to join different filament. Have you?
No, I never finished that project. I got distracted by something else. The parts are still sitting here on my desk. Yeah, that I was going to build a jig. Yeah, but that also could get into, you know, there's things you can buy if you're trying to do arty stuff that's different colors. There's different ways to try to get the different color filaments, either to splice them all together at the appropriate point and have a single print head, or to have, you know, multiple extruders, multiple nozzles doing the different colors, plastics and stuff. And that all involves trying to, or some of that involves, you know, splicing the material together. But yeah, that's why I said if you're hardcore, you know, to make your own filament, that's like a whole nother set of machining and stuff to get that tolerance going.
Yeah, but for most people, actually, I don't think, well, or rather, I think that the activation hurdle to overcome to get a 3D printer just for astrophotography is a little high. Okay, so what I would say is you should really take a step back and ask yourself, what can I do with a 3D printer, and how much are they costing? So the baseline bottom line is a really good one, the one which I showed you, which is an entry model and fully expandable, can be modified to print all sorts of different filaments, costs only about $200. Okay, and so you're not really risking a lot of money there. And then you what you can actually do with it, or what I found out is not just print things for astrophotography, but all that stuff which breaks around the house all the time. You can just design your own replacement parts and fix them. You don't have to go out, drive around. You save a lot of time doing this, and you save a lot of money. So I've calculated up the parts which I've printed so far in order to keep things going here in the house. Pool, I have the pool pump going. I have pool light installed because the old one was broken, etc. Pieces for my car. When I add all of this up, I have calculated that I've probably saved about $4,000 in the meantime in the last 2 years simply on parts which I've 3D printed myself. Okay, so that's what I would consider first. Right? This thing is just like, as I said, an inkjet printer. It's a very clunky one. It prints one layer, then the printhead moves. Instead of spitting out the paper, now the printhead simply moves 0.2 millimeters in the z-axis and prints the next layer on top of it. And they're just fusing together. That's the entire principle of it. So it's not really an incredibly complex thing which you have to worry about. It's very easy to get into, and you can very quickly actually get the hang of it.
Has anyone here used a resin printer, 3D printer?
Sorry?
Resin printer. No, I haven't. It looks messy.
Yes, I've been eyeing. I like the resolution, at least from what I've seen online. But yes, there's a whole cleanup process, and then you have to cure again with UV afterwards to strengthen the part. But that's all I've just seen online. So I don't have any first-hand experience.
Yeah, my impression is if you're trying to do small artsy stuff, that's what you want, but for big gross mechanical things, that the other style is preferred, I think.
And one other question: who of you has grandchildren?
No, I.
Okay, well, I mean, you can do all sorts of stuff. You know, this is rocket model, the 7.5. Which you can just basically download the files for. And I ran that one through my 3D printer. So you can make all sorts of toys for the kids with that also. And I've made a bunch of stuff for the kids of friends. They all love me now. They all want to be adopted.
So out of curiosity, how long does it take to print something like your Saturn V?
That one takes about 24 to 30 hours.
Cool.
A lot of time. Yeah.
Really
Was it one shot or multiple phases, and then you glued it together?
That's actually 4 pieces, but nothing is glued, just stuck together.
Okay.
Yeah, the real problem, as I was mentioning before, of 3D printing is that, of course, the 3D printer head cannot print on air. So if you have overhang, you have to organize for some sort of throwaway support that keep the overhang and the printer can work on it, because otherwise you are in trouble.
Yeah, I understand.
For me, is the biggest limitation of the technology. Actually, there are solutions. There are 3D printer with the dual head that can print special material that can be soluble. So you print virtually, you print a complete solid object, and you put in water or in other chemicals, depending on the material that you use for the support, and the support disappear, and you remain with the void that you need for the overhang.
I have a different question. You guys seem to have pretty large print beds. I don't. So do you have any like local makerspace that I can perhaps go to and find a bigger printer to like do the job for me? Like locally as local to San Jose or maybe Santa Clara, something like that?
I don't know anything.
There may be Maker Nexus in Sunnyvale. They may have 3D printers.
Yes, that's true. That's true. That's true.
Oh, make it Nexus. Yeah, I've never been there, but yeah, okay.
I have a
Thank
question about Glenn and Paolo mentioned threaded adapters. So is the 3D printer precise enough to print a thread that would then mesh with like a thread made on a lathe, or do you have to use then a tap and die to chase the thread?
No, we print threads.
No, we print threads. The difficult part that was the things that Glenn mentioned was to create a sort of library, or better, modify the data of an existing library in order to cover all the typical fine thread that are in the astronomical business. And
right. Glenn mentioned
5 or something like that. Yeah,
Yeah,
but the printer has a 0.1 millimeter resolution.
okay. Yeah, because Glenn mentioned a thread that was as small as 0.6 millimeter pitch. So that basically you only have 6 segments in a full 360 degrees, right?
Yes, of course, with a lathe, you can have a better thread. There is nothing to that, of course. With metal and a lathe, you can have a real precise thread. That's a decent thread. I mean, I will not attach 5 kilos of $10,000 camera to that thread, but I mean.
But a filter, for instance, is not heavy, so that should be sufficient, right?
No, but you might, if maybe you're prototyping something that you're going to get a precise parts for or something. So you might have your camera and filter wheel and everything hanging, but you put some string or something so that if you have a catastrophic failure, it won't, fall all the way to the concrete or something. But, I've learned, like I said, I was doing things kind of in solid plastic, but and Paolo's doing the thick ribs. I think we've learned, there's a couple different ways that these parts can fail, and one is making sure that the finished diameter, outside diameter of the threads, or inside diameter, depending on male or female, is actually correct. Is one, because if it's slightly too small, then it could strip out, right? And the other one is just making the whole thing strong enough so that it doesn't fail. If you have a big 3D printed part and you can squeeze it and hear kind of a crackling noise, that's the infill failing, right? And so if you've got that, then that's a sign that it could fail. So I've switched to printing, and it's a trade-off between print speed and strength, right? But so the parts I'm really worried about, I print in solid nylon fiber. So yeah, it might have taken 55 hours, but I could stand on it, and it's not gonna fail.
And also another let's say trick is to have an enclosure, because the enclosure creates a warm environment, and the filament has more time to stick to the previous layer, because one other problem is the delamination of layer. So you have all these layer, and at a certain moment you have a crack in the middle of the layer, because the layer are not stick together enough. And that's the enclosure is important. I made, for instance, let's say a plastic enclosure that is enough to create a stable warm environment, especially when I print with ASA. that is like ABS or like carbon fiber needs a high temperature.
So that's using temperature when you're printing to help with adhesion of the layers, better adhesion of the layers. What about after the fact? Which material has the least impact on from temperature? So if you're in a very cold environment, does it impact PLA different versus ABS different versus ASA versus I mean, would you get warping in any of these plastics or?
Yes, yes. The PLA is the one that warps the most, is more sensible to the temperature, or better, as what they call a glass point, the point under of the temperature underneath that the plastic becomes solid. Over that point, with that temperature, the plastic becomes softer. It's not melting, but you can apply that. And for the PLA is relatively soft. If I remember well, 75, 80 degrees Celsius. Instead, for other, you are talking for PETG and ABS or ASA. We are talking about 130, 150 degrees.
What about in the opposite direction? Getting colder?
Colder? I don't know. Honestly, in terms of resistance in freezing temperature, so below zero, if they become brittle or these kind of things, that's your question. I don't know the answer.
So
We've thought more about the resistance to UV light outside, and so the ABS and the ASA and the carbon fiber are all known to be stable outside, and but they all have a certain amount of issues that make it harder to print, which is the warping, like you mentioned, especially if you don't have an enclosure. And some are better than others. ABS is notorious for being horrible to work with, but it produces a real stable part that's UV resistant. And
I guess what I was trying to get at is if you have something that's holding your camera and at room temperature, everything's aligned, but let's say it got really cold, would it warp the plastic any such that now it's not aligned? Is that substantial enough or negligible?
Not that I know.
Yeah, I haven't had any issues. A lot of this has been in the guide scopes, but like in the case of the Vixen, that's it's holding everything on the imaging train. But yeah, I haven't noticed any issues.
I guess there's a question in the comments from Karen who left, but I'll ask her question. So what about like noxious chemicals and things like that? Is there a problem with melting plastic inside your house?
Yes, ABS. That's the reason why ASA is better than ABS, because ABS, you have to have an enclosure, and possibly you have to have ventilation to outside, because the melted plastic is smelly, let's say. And I don't know exactly the chemicals that are in that smell, but for sure are not good for your lungs. But for the other, instead, the PLA smell of caramel, roasted sugar, because it's based on sugar. That's the reason why it's biodegradable, the PLA. The other plastic, PETG and ASA, are very, very, very mild smelly, and as far as I know, are not considered toxic. ABS, yes. I have no experience, and Glenn we can answer about the carbon fiber.
Yeah, it doesn't really have a strong odor, but I imagine you want to think about where you put your 3D printer, and maybe more for noise than smell. If it's going to be printing overnight, you don't want it next to your bed. It can kind of sound like people having a conversation in another room or something, where you just can't quite figure out what they're saying, but it sounds like they're saying something. And so, all the different noises it makes the patterns. Yeah.
Joe, do you have a point of view? I mean, you actually know something about this medicine. Joe's a medical researcher in his spare time.
Well, the PLA, I'm just printing inside my office. It's actually not really noisy. That Ender 3 basic baseline entry model printer is actually fairly quiet. So I can print through the entire day and still work on my computer without being distracted. And also, as it's basically polylactic acid, toxicity of that is very low, if any.
Yeah.
And it's actually the cheapest. I mean, it's the cheapest entry-level material, and works for most things. Yes, I mean, if you're gonna expose it to heat, that is perhaps some issue. But it's probably the cheapest material. And for prototyping or getting into this and trying out, what you can actually do, I think that's the perfect material. Not complicated, very easy to handle. And once you want to do some more complex stuff with more structural requirement, then you can change to other materials. I would look at 3D printing not with this big hurdle, but it's really is going to be a very easy way into that hobby. And
Joe,
you can expand anytime.
Joe, I'm using the PLA for all the boxes for my little project around the telescope and around the house. And of course, my grandson, 9 years old, is using the PLA for all his project, because let's say more than a 3D printer, mine is a condominium, part mine and part used by my grandson for his stuff that he designed with Tinkercad.
All right. Do we have any more questions for this distinguished panel?
I have one question, but that can probably be taken offline, and that's regarding on the electronic side. I know some of you guys are using motors and then interfacing them with controller boards and then making them talk with ECOS or whichever other software. I guess that I would love to learn more about at a later point, not necessarily right now, but I don't know who to start with.
I mean, we have a little time if somebody wants to address it.
Well, the Arduinos are pretty easy.
Yeah.
And I guess Raspberry Pi is probably more involved because you've got, a whole operating system and everything to deal with. But, there's kind of like the 3D printing, there's all of these people that have gone before and have posted their sketches, they're called, for the Arduino, on GitHub or whatever, on different sites, Instructables. So you might not have to design your own focus controller sketch and hardware. It's probably already out there, right? And so that's the way that I got started with it.
Yeah, for instance, the flip flap that I'm using has an Arduino inside and the servo motor, a normal RC servo motor for moving the cover, and the sketch, the program. I started from an existing one because was interesting from the fact that that was let's say simulation of the existing flip-flap cover, and that was easy because at that point I can use the standard driver in ASCOM or Indy, and I was able to work with ECOS. Now I'm using Nina, and I'm using that, and then without problem. And I modified, of course, because I want to change the speed of the movement, this and the other. But basically, the interface, the API of interface with the driver remained the same, and that was easy. But basically, yes, Arduino is the way to go for the little motor and this kind of thing, because exists also a bunch of other little board that you can use for interfacing, stepping motor, temperature.
Yeah, those I'm aware of. I think it was just taking it further, right? So going beyond just the board and what you're putting together with the Arduino, but now it's taking it further and saying, how do I interface that with, you know, with the ECOS protocol or whatever it might be? How do you connect those together, right? I think those are, but you know, a conversation for later, perhaps.
Well, from what I showed, the driver, well, the sketch for the Arduino is called My Focuser Pro. And that's freely available, and that is has a driver which is directly built into ECOS. So that really is no issue at all. You know, you just select a drop-down menu, and it works basically out of the box. So the only thing I actually modified in that sketch was the number of steps and it could take and the upper limits. The rest was already there.
Yeah.
Okay, sounds like we're good on questions for the 3D printing group. I have one more question. It's only remotely connected, but you see these, you know, this house was 3D printed. Like, what does that mean? I mean, I don't understand that concept. And like, you know, is there some kind of gigantic 3D printer with a hose coming out shooting plastic, or
cement?
Cement.
So is that what it means?
Well, I think it can mean different things to different people that are trying to make a point, but yeah, I mean, so for rapid construction or you know, constructing things out of moon regolith or something, right? They're experimenting with the same additive manufacturing FDM technology, but with different materials like cement or composited regolith or whatever, right?
Okay, all right.
Yeah.
In general, the same concept.
Yeah, there are some really big 3D printers, room size.
All right.
Yeah.
Well, my last question sort of to the group is future meetings. Like, are there topics that are, I mean, I guess I can start a thread on the imaging mailing list, but are there other topics? It seemed like this was an interesting topic for folks. A lot of people at least RSVP'd and many showed up. Are there, think about if there are other topics, feel free to say it now, or we can talk about it on email or where we have panels and discuss things.
Yeah, I know I brought this up to Glenn in the past, but you know, I'd like to bring it up to the entire panel. I'm new getting into astroimaging, so from visual to now starting to dip my toes a little. Well, actually, now I'm knee deep, right, Glenn?
Yeah.
But one of the things that I'm trying to figure out for myself, what kind of workflow do I need to start learning, right? What are the different softwares? How do people go through their workflow? I don't know if we have any documentation that different folks have put their entire workflow down, so someone could learn from. Oh, okay, so let's say Paolo does this, and this, all the way from start to end. You know, Glenn does this, Joe does this. You know, I think that would be very useful for folks just starting to learn.
Yeah, that's kind of how I started out on my YouTube channel, and all that stuff is really aging now because it's, first of all, it was DSLR, and things have changed so much in the meantime from about 2016 till now. But yeah, it's almost that there's so many choices now, right? There, it used to be, backyard EOS and SGP, and that was about it. But now you've got Nina, and you've got, ASI Air, and Stellar Mate, and Ecos, and Voyager, and on and on and on, right? So there's lots of choices now. So it's hard to, if I picked a workflow to explain, then somebody else would say, well, I'm using Nina or whatever. So it would be different. But I mean, so the basic concepts apply across all of them, right? I mean, you need to plate solve, and you need to come to focus, and you need to auto guide and dither, and so some of that applies. But yeah, one challenge would be now the plethora of choices. But one thing I thought, I want to change my program for the public. I'm tired of giving the same old lecture that I've given for 2-3 years now, every month. And I'd like to work with Hai on a Ecos presentation, and Francesco on a Nina presentation, and I can do SGP, and so that kind of thing. Sort of pre-produce those, or have guest lectures, or whatever. Now that we're finally getting somewhat close to having public events again, at least on the imaging side.
And Francesco did a few lectures there, probably
on Nina.
Recorded. I'm not talking about that one though. On Pix Insight.
Pix Insight, yeah.
Francesco recorded. I'm sure they were recorded. I watched them live, but are they around, either Glenn or Francesco?
We had some technical challenges at one or more of them, I think.
Oh, wow.
It was before the Zoom era,
Anyway, so the introduction to imaging is a topic of its own, right?
Yeah. So go. Yeah. So content that's already there, right? And I had showed my QR codes and links, but I have a channel. The SJAA has a channel. So there's a lot of material there, but certainly, yeah, we can cover whatever people want to talk about.
If folks are willing, I can maybe try to connect with folks separately and start putting some, just at least workflow listings of what people use. And that might be a good library of at least collecting what are all the different kinds of things people do and use in their workflows. That might be helpful to someone. I know it'll be helpful to me.
Sure. Yeah.
One other possible things that I think that is interesting also to the people that start these kind of things is the choice of the hardware, because there are so many choices in the hardware, and each one of us had made mistake, and trying to put together all these kind of mistake in a, let's say, troubleshooting or FAQ or something like that, at least that will be, I think, interesting also. Especially hardware respect, let's say, the money that you want to spend, the respect of the condition that you want to observe or photograph. Because many times you end up with something that is good for, Bortle 3 area, but you end up having a beautiful piece of hardware, is a piece of optics, and use in downtown San Jose, and that's point you are throwing away money, something like that.
All right. Well, I tell you what, it's been an hour and a quarter. And I said I was going to keep it to an hour and a quarter and to an hour and a half. So why don't we do my first meeting? We'll call it a day. And we'll come back next month with some topic, and I'll start a email thread and send suggestions, or I'll come up with something like the way Bruce always did, if not. And thanks, especially thanks our three presenters, our three panelists. I really thought that was an amazing presentation. Let's give them a hand. Unmute yourself and give them a hand in fact. So I'll see you guys next month. So thank you.
Thanks.
Thank you. Bye.
Bye.
Bye, everyone.
Thank you.
Bye.